Esters, the stuff that smells really good and really bad at the same time. An ester is a hydrocarbon that contains a COO group. That's called an ester group. The general formula for an ester is R, C, double bond O, O, R prime. Remember that R just means any length of a carbon chain. We refer to that as an alkyl group. R and R prime, the reason why there's a prime symbol there is because the two R groups, the two alkyl chains, do not have to be the same. An example of an ester is CH3, CH2, carbonyl, OCH3. You can think of an ester as a carboxylic acid, but not on the first or last carbon. It's kind of like a carboxylic acid in the middle of a chain. The names of esters, very annoyingly so, end in O8, which has nothing to do with its original family name. The way we go about naming this is we look at the two carbon chains we have on an ester, which is interrupted by this oxygen here. So looking at the ester, we always have a carbon chain on the right side of this O in this picture here, and then another carbon chain on the other side of the O on the left side in this picture here. We name those separately. The first one we name is the carbon chain that's directly attached to the oxygen, and that's this one here. This is a 2 carbon chain. That's going to be ethyl. The second part of the name is going to be this carbon chain here, which one of the carbons is actually taking part in the carbonyl group. We see that in this example, there's also 2 carbons, so this is another ethyl. Now the last word in an ester name ends in O8, so this is called ethyl ethanoate. Ethyl ethanoate. And unlike the previous names that we've looked at, this is actually 2 words. Let's try another one. Here's another ester, and remember the carbon chain is interrupted by this little oxygen in the middle. On one side, we have this. On the other side, we have that. We always name the one that doesn't have the carbonyl first, or the one that's attached to the O directly first. So this is going to be propyl for 3. And on the other side here, we have another 3 carbon chain, propanoate. Let's look at some line diagrams. Line diagrams are no different. First, we name the thing that's attached to the O directly. That's this guy over here. We count the carbons. It looks like we have 1, 2, 3, 4, 5 carbons. So the name of this is going to be pentyl to start. On the other side, we have 1, 2 carbons. So this is pentyl ethanoate. Don't be fooled if the ester does not look like the general formula for an ester. This one happens to be upside down and flipped over, but that's alright. Same rules apply. First, we name the section that's attached to the oxygen. That's that one there. We see that we have 1, 2, 3, 4 carbons. So this is going to be butyl. On the other side of the oxygen, we have 1, 2 carbons, and this is butyl ethanoate. Even if the chain is all twisty-turny, same procedure again. We look at the chain attached to the O, that's this one on this side. We have 1, 2, 3, 4, 5 carbons in total, so this is pentyl. On the other side, what the carbonyl is, we have 1, 2, 3, 4, 5. So this is pentyl pentanoate. Okay. Esters are fairly easy to name as long as you know which branch goes first. The one attached to the O goes first, followed by the one attached to the carbonyl. The names will not get any harder than this. We will not be testing anything that have branches on it. So no esters with branches on them will be asked of you. Those get a little bit more complicated to name. So we only focus on the simple ones that have no branches. Now, organic chemistry is not about naming. Naming is just what we learn in high school to get you ready for the real organic chemistry, which is all about chemical reactions. Chemical reactions. Okay? There are hundreds upon hundreds of chemical reactions that you have to learn and memorize in university, But in high school, we just give you one. And the one that we give you is the synthesis of an ester. How on earth do we make those things? How do people make perfumes? Well, esters are synthesized by combining a carboxylic acid with an alcohol. Should make sense because carboxylic acids kind of look similar to esters, but they're in the middle. Esters in the middle, carboxylic acid is in the first or last carbon. Shouldn't be a surprise that carboxylic acid is used to fuse with something else to put that C double bond OO grouping in the middle of a structure. This reaction needs to happen in the presence of acid. Acid H plus. I write H plus because H's are what make an acid, but we can put bracket acid to remind you of that. Okay, so this is happening in the presence of an acid, which acts as a catalyst to make the reaction go a bit faster. So this is how the reaction works. First, I'm going to do a general formula, general case for you. We have, here is the carboxylic acid. We're going to add that to an alcohol. An alcohol, remember, is just an OH group coming off of any alkyl branch or chain. In the presence of an acid, we write the H plus on top of the arrow to show that it's not part of the reaction, but just a catalyst. And our final product that we get out is an ester and water. It kind of looks like the R prime from the alcohol just attaches itself to the O of the carboxylic acid. Now here is what actually happens. The OH from the carboxylic acid falls off and combines with the H from the alcohol. OHH, what's that? That gets you the water. And then the remaining parts of those two reactants fuse together to make the ester. So here's an example. Here we have ethanoic acid or acetic acid. And let's put that together with ethanol like this. In the presence of an acid, what's going to happen? Well, the OH is going to fall off from the carboxylic acid and fuse together with the H on the alcohol, and then the two remaining structures fuse together. So we have CH3, C, double bond O, O, CH2, CH3, plus water. And again, the water is coming from a combination of the OH from the acid with the H from the alcohol. Do you see that this piece here is right here? We're literally fusing these molecules together. Okay, let's do some examples with line diagrams. So in fusing these things, here we have the carboxylic acid, here is the alcohol. The OH from the carboxylic acid falls off, so we have this left over here. The O and the rest of the alcohol will fuse onto that. So here is the O. This O is this O. On this O, we have a 1, 2, 3 carbon chain. So on the final product, we will draw a 1, 2, 3 carbon chain. And of course, our other product is water. Okay, next example. Here we have the acid and then the alcohol. Once again, we look, remember what happens to the acid. The OH falls off. So once it falls off, we have this structure like this. Okay, then the alcohol will fuse on. So the alcohol, the O is right there. So that's going to be this O here. Then the O is attached to a aromatic ring. So all we have to do is draw an aromatic ring attached to that O. And then put down water. Easy? Yes. I'm glad you agree. Last example. Here is the acid. The OH falls off. So we are left with this portion of that molecule. The alcohol gets on there. So there's the O. That's this one here. These two O's are the same. Now, what is that O attached to? My goodness. Well, it's attached to 1, 2, 3, 4, 5 carbons. So we're going to draw that. 1, 2, 3, 4, 5 carbons. We're going to maintain that cis branch for the alkene there. Then we see a ethyl group coming off of that cis double bond. Like that. Plus water. Okay? Now, organic chemistry is about reactions, like I said, but most notably, organic chemistry is about how to coming up with ways to make particular molecules. For example, a biologist discovers a plant that miraculously cures or relieves arthritis. And the biologist says, well, it would be kind of stupid to grow so many plants to harvest them every year just to relieve arthritis. That's not really efficient, and it's pretty costly to do that. That's a lot of land needed for arthritis. So the biologist goes and doing some chemistry, he or she is going to isolate the actual chemical compound from that plant that is doing the work on arthritis. And let's say the person goes, Eureka, I found it. There it is. That's what it looks like. The biologist brings that molecule to an organic chemist and says, please make me this molecule. Please synthesize it so that we can make it an industrial process and make this drug on a large scale. And then the organic chemist goes, well, this molecule that you have, sir, is an ester. And I know how esters are made. They're combining carboxylic acid with an alcohol. So the organic chemist goes into his lab and he tries to synthesize this compound. What are the two reactants that organic chemists need to have? Well, he or she needs to have a carboxylic acid. What is a carboxylic acid? Well, we know that this oxygen is coming from an alcohol. So the carboxylic acid is whatever is on the left side of the molecule we're trying to make. So the carboxylic acid that we need is going to look like this. Okay. The alcohol is coming from the right side of that ester. And the alcohol, remember, is something with an OH group. And then this part of the ester is going to be the thing that the alcohol brings in, like so. And there you have it. We have just industrialized a process for making that compound which relieves arthritis. That's not actually the compound that cures arthritis, guys. That's not it. But it's an analogy for you to learn how organic chemistry works. In real life, often the compounds we discover in plants are enormous. They're huge, they're cyclic, they have isomers to them, they have things that bend inwards and outwards, and the steps we need to make that compound is actually quite lengthy and quite difficult. And it's the organic chemist's job to figure out all the different reactions that piece together to make the final product. It's a very difficult thing to do, but if you like piecing puzzles together and solving these cool riddles, you can consider going into pharmacology, which is the branch of science that deal with synthesis of multiple compounds. Much more cool than a pharmacist, right? You get to actually make the drugs. All right, next one. Here's an ester. Everything on this side is coming from the carboxylic acid. You can even just draw them upside down because that helps you visualize what's happening. No worries there. So that's the carboxylic acid. Everything on the other side of the carbonyl is coming from the alcohol. So we have here, see this O here is just that O right there. The alcohol is attached to 1, 2, 3, and then a cyclic pentagon, like so. And for our final example, everything on this side is from the carboxylic acid. So we are getting this structure. Everything on the other side is coming from the alcohol. So we have this 1, 2, 3, 4, 5, 6 double bond on the first hump. There we go. Add the H.O to make it into an alcohol. Okay, doesn't matter what you write first, acid or alcohol, doesn't matter if you turn them or flip them upside down, whatever helps you visualize what's happening to synthesize the final product, you can draw it in whichever orientation you want. A plus B is equal to B plus A, right? It's all the same. Okay, so this is the only reaction in organic chemistry that we will study. Learn how to make esters and learn how to break them down to see what they were made of in the first place. Goo out.